All right, today's our last day of lecture before we review tomorrow and take an exam on Friday. So we'll get into it. We have an assignment due tonight. Hopefully people are starting to think about implementing CYK. Because this has been news to everyone I've talked to in my office, please do look at the actual project assignment. It's not just a repository for the program. There are actually input and output files for you to test, as well as so you know the associated input format, you know what output you should be producing, you have a test case, and then I also link to a CYK simulator on the web, and that helps you to visualize what cells your program should be referring to as you build up the answers to each of those cells using dynamic programming. So I highly recommend you look at that and utilize that to help you with debugging. That will be useful. Questions about where we are? The class is pretty straightforward. It does kind of feel like a math class, but it just has a very nice structure that I'm very happy with. Nothing totally out of left field. I don't know how that term came to be, because left fielders have really poor arms.
That to throw from left to first is really fun.
Why would you throw from left to first unless you're trying to double someone up?
That's the first guy.
You want the person with the good arm, it's out of right field.
Left. Isn't it from the home plate's perspective? Whatever.
Apparently, I'm really distracted today. The ADDAF thing I have in my office pointed toward the door is actually, I'm starting that today. So last we were talking about countable sets. We talked about that the positive integers and the positive even integers are countable for fairly obvious reasons. There's a place to start, and there's a successor function that can generate, given a current one, what is the next one? And they're infinitely countable sets. But we talked about how the set of all integers could be countable. And this was just starting with the initial value 0 and then alternating positive to negative, and every pair of that increasing the absolute value by 1. So going from 0 to 1, -1, 2, -2, 3, -3. And you could come up with a function that, given an input, could tell you which number that is. In fact, I want to stop here and come up with that function because I think there is value to that. So let's write, this is very similar to a program, except instead of a program, it's going to be a function that's going to take an integer. Sorry, it's going to take a, integer. And it is going to spit out a positive integer. Or it can be vice versa. It doesn't really matter which way you go. You can take the positive integer and spit out an integer. The idea is we want to map these sets onto each other with some kind of function. Let's actually go this way. I think that will be slightly easier to see. So we're going to take an index and we want to map that onto the associated integer in that set. So as we count up the positive integers from 1, 2, 3, 4, 5, etc., we want to map this onto 0, 1, -1, 2, -2, etc. So what is the mathematical function that does that? Just to get a sense of how math intuitive are our upper division computer science students. Yes. Now, that doesn't necessarily have to completely be linear, but there will be two components to it, one of which is linear.
I mean, if you divide whatever the other than 0, but if you divide whatever the number is by 2, if you end up having a whole digit, then it's a positive integer. If you have a non-whole digit, then it's a negative integer.
Yep. How do we represent that mathematically? That's exactly it. There's the logic. So first thing to recognize is if we ignored the sign, what would the solution be?
X divided by 2.4, X divided by 2.
Yeah. So if we're trying to say we're gonna go from this value to, let's get these values of some kind. So we're gonna go from that's part of it. Now, how do we deal with the sign?
Let's do it, X mod 2.
There's no if in a math function. How do we alternate? So in code, you use mod 2 and check mod 2 equals 0. That's going to yes, no, yes, no, yes, no, yes, no. In math, how do we go positive, negative, positive, negative, positive, negative?
Negative 1 to the power of.
Yes. Do we want to the x? Do we want the first one to be, so the first time we do this, x is 1. To be able to generate that 0. Do we want that 1 to produce something that is negative or positive?
Well, it's 0.
Yeah, it doesn't matter, but according to this pattern, negative, negative, negative 0 is the same thing as 0. So that works for us. So this is it.
Yeah.
We're done. If this was challenging, our CS curriculum is not doing you any benefits. We need to work on how mathematically we introduce some of our content. But yeah, the idea here is that if you can map the set of all integers or the set of positive integers onto some other set, then you have infinities of the same size. We'll get to that, but they're also countable because you can immediately create a function that maps one onto the other. So by definition, it is countable. We were talking about at the very end of the last class, the set of all rational numbers, and we came up with the answer that this was countable. And the way that it was countable, you had to use an intelligent algorithm to do it. We had this idea that we could maybe represent this in 2 dimensions. So the way that I'm going to draw this is we have the positive integers in one direction. We'll have the positive integers in the other direction. How could we represent the set of all rational numbers with this? We just this would iterate this entire table. Does it ever do anything negative? Imagine just overlaying one of these tables with a -1 on top of it. Whenever we finish one of these, we just do the -1, one of these, the -1, one of these, the -1, and that would work. So the idea is it doesn't really matter how many dimensions there are, as long as there is a positive number of dimensions, you can kind of like that 2-dimensional Turing machine and a spiral. You can find a way to navigate that space such that the idea is that you could not give me a rational number that I could not eventually reach by iterating this table in this fashion. Because these both go on forever, if I decide to iterate it like this row never ends. So we never get here. This would just be either your numerator and denominator, or vice versa, it doesn't really matter which, but now we have a fraction from this table, and whatever fraction you give me, I can tell you how many numbers we would look at before we revealed that fraction. I don't care what the numerator and denominator of that fraction is, this process will eventually get to that fraction. Does everyone agree with that statement? Does that work? Does everyone understand the concept? I won't make you come up with the function for this, but we could do it. To say, you give me a fraction, I tell you the first time that we reveal that fraction in this table. Because there are equivalences, like 2 over 2 is the same as 1 over 1. Everything on this diagonal has the same mathematical value. That turns out not to matter. We already answered this, but let's ask someone who didn't answer this last time. What is a set that is uncountable? We can use the same answer from last time, but who remembers what that answer was?
Irrational numbers?
Yeah, so another term for, well, some irrational numbers would be reals, but being able to count the reals. So let's ask, is the set of real numbers countable? Do people agree, just without going into it, that the set of real numbers is not countable? Or if so, how do you visualize that, or how do you understand why is it not countable? Yeah,
Because you wouldn't be able to count a subset.
in what sense? That is right, but
So for example, if
the
you.
reals between 0 and 1, for instance,
That's
yeah,
actually what I was saying.
yeah. So how could we go about that? Are there any ideas or algorithms? Say, let's assume that it is countable. If it is countable, then there exists an algorithm that will enumerate all of the reals between 0 and 1. How would you do that?
No matter what size of step you choose, I can choose a small step.
Sure. How about a process like, so there's not necessarily a great place to start, right? But imagine being able to iterate all of the decimals of length 1. 0.1, 0, 0.1, 0.2, 0.3. When we're done with that, let's iterate all decimals of length 2. When we're done with that, let's iterate decimals of length 3. When we're done with that, let's iterate decimals of length 4. What does that not include? Any infinite length number that doesn't repeat? So something like that would include the square root of 2. That's between 1 and 2, not between 0 and 1, but you could come up with another irrational number that that process would never get to. A mathematical concept that is a real number between 0 and 1 that this process does not ever get to, regardless of the number of steps that it takes. I'll show you a more elegant proof of that in a bit, but why we care to distinguish between countable and uncountable sets is this actually perfectly maps onto an algorithmic concept of the classes of programs that can terminate or not terminate, which is of much more interest and importance to computer scientists. There becomes an enumeration procedure for all countably infinite sets that says if the answer is out there, this algorithm will terminate and find it. Only if the answer is not out there will this process go forever. And that is an interesting class of types of programs that we could write. They're not algorithms because algorithms guarantee termination. At some point, it may be long after the Earth is gone, but there's another class of algorithms that can answer yes, but cannot answer no, or can answer no, but cannot answer yes. And we would never know if the answer is no, we just haven't gotten there yet. Kind of like, does pi have repeating digits? If we ever find those repeating digits, we can go exactly with that knowledge prove it. But if we don't ever find those, we don't know if we just haven't discovered it yet, or if it does go on forever. It's also important because now this maps directly onto a Turing machine. We can make a program for it, but we don't know whether or not that program will terminate. So let's say the set is all strings from the alphabet that contain one or more of these characters. Repeated some number of times. Do we agree first that this is an infinite set?
Yes.
Is it countable? Is there a way that we could enumerate all of those strings? And no matter what string you give me, I can tell you the position in that algorithm that generates it, the step of that algorithm that generates that string. Note that there are some processes here that would not make this complete and countable. The question is there a process that makes it countable? So for instance, I could iterate and continue generating new strings if I said etc. That process would never terminate, and it would continue to generate new strings that are in sigma plus. On the other hand, will it ever produce the string B? No. So is there a process that does? Who wants to tell me if you think there is one?
I mean, you can use it like a queue, right? So then you check all string lengths of like 1. and you
Yeah.
Push those back, and then you do those for string lengths 2, and you push those back in the queue.
So we could generate everything of string length 1, A, B, and C. What are all of those of length 2? A, B, B, C, and yeah, this is just a recursive procedure, taking that and then appending all of those to the end of that. And then B, A, B, and B, C, etc. And there would be 3 of these. How many are there of these? 3 squared. There'd be 3 cubed of the next, 3 to the 4th of the next, 3 to the 5th of the next. Is that complete? Is there any string that this process would fail to generate that adheres to sigma plus?
It would eventually get there.
It would eventually get there. We don't care about efficiency right now. We just care about, is this process countable? Is it complete? We're going to move into a part of this class that is more theoretical, but it's also kind of saying, with infinite compute power, what could we answer and what could we not? We've kind of determined the limitations of the modern computer by saying, what can a Turing machine do? But we don't really have a concept of, if we had infinite compute power, what could a Turing machine still do? We have limitations based on modern compute power, which is why we care about things like exponential complexity versus polynomial time complexity. Assuming we had infinite complexity, what would be, or infinite power, what would be possible? What would Palpatine get really excited about? I apologize for those who don't know the reference. So, listing all strings in alphabetical order, yeah.
I know that we were talking about Alan Turing last class.
Yeah.
In his day, was it like the concepts of non-determinism, was that even like something people thought about?
Yeah, people had thought about determinism versus non-determinism before we had a computer, before we had, in math, the concept of how much work is it to answer this question.
Interesting. We're thinking about that, so about computers.
Yeah, universities were very different back in the day. Society was very different back in the day. I speak like I was there, I was not. I'm not that old.
Thanks to clarify.
Right. In case you weren't aware, I'm not hundreds of years old. Maybe universities have changed, and maybe it's just in the professor's eyes. I think that my students think that I'm hundreds of years old.
This is my Palpatine. Secretly a Force Lich.
Is he an idol of mine? Just a little bit.
Shocking.
So, yeah. If we do this alphabetically, we will not have a process that terminates. But if we list them in length order, now we do have an enumeration procedure. We're gonna call this an enumeration procedure, an algorithm that we could write that would enumerate this infinitely countable set and eventually produce any given query. It doesn't produce everything in the set because the set is infinite. That procedure would not terminate, but it is an enumeration procedure because no matter what element of the set you tell me, I could tell you how long it takes to generate it or how many, which step it generates it on. And there is nothing that you could give me where I would not have that associated answer for you. So yes, important results are that Turing machines are countable. That's really weird to think about because in a very similar way to this set, if you were to list all sets of possible Turing machines, some way of breaking Turing machines down into an associated binary component, like here is this Turing machine. These states and these transitions are represented as a string. And then I attach to the end of that the part of the input tape that is relevant. I would end up with some string that could be represented in some language like this. And if I just generated, some of those would be valid Turing machines and some of them would not. But we would have an enumeration procedure that could just continue to spit out binary strings, some of which would represent valid Turing machine configurations and some of which would not. It's a procedure that could generate every algorithm that you could possibly write. Is this efficient? Hell no.
Like the monkey typewriter thing.
Kind of. So that's just an aside for the moment. We're going to come back and talk about that in a little bit more detail in a bit, but that's kind of a glimpse into the abstract future that we're going to visit for a bit. Yeah.
And that was an offshoot of the universal Turing.
Yeah. Yeah, a Turing machine that could recognize other Turing machines. But because Turing machines are countable, we can also prove that the universal Turing machine would recognize or be able to recognize any valid Turing machine because they're countable. So let's talk about a subclass of Turing machines called a linear bounded automata. So we found that we could extend the power of a Turing machine without really changing the underlying power. We just change the power of the representation. But are there any fun ways that we could start with the base of a Turing machine and limit it in ways that actually tell us or inform us of something interesting? So one way of this is more efficient acceptance or rejection. That's something that we might care about. Turing machines aren't particularly efficient in their base form. So it would be nice if we could restrict the class of languages that it accepts, and as a trade-off for that restriction, get increased efficiency, better runtimes. So we have found that a non-deterministic pushdown automata is really just a non-deterministic Turing machine where the tape is restricted to be interacted with like a stack. We can't just jump around wherever we want. We can only move and read from the most recent symbol that we got to on the tape. So we start with nothing on the tape, and we can put things on the tape and take things off the tape, but only in that kind of stack-like manipulation. The other really important limitation to a Turing machine is just limiting access to a finite portion of the tape. This simulates the idea of limited memory in ways that is very realistic, because no machine that we run programs on has infinite memory. So if we limited access to just some amount of the tape, this would be the equivalent of saying, can you solve this problem with this amount of memory? The way this is going to be useful to us is that we want to find the class of languages that can be solved with the amount of memory that's represented by the size of the input of the problem. So if we have a certain amount of memory that is needed to represent the string, what classes of languages could we accept if we did not or could not use more memory than that input? We no longer restrict things to be like a stack, so we can move around freely, but you can only start at the first character, end at the last character, and freely change things among that input. But if you change something from the input, you've lost what that used to be, unless you have some other way of storing it within that input. So that's the equivalence to a finite state machine. So we're relating the classes that we've seen so far to what changes would you have to make to a Turing machine to simulate an NPDA, using it like an infinite stack, or the finite amount of memory that is the size of the input, a finite amount of tape space, that's a DFA NFA. So sorry, this was separate from the input. I was trying to jump ahead of myself. So a DFA or NFA would have a limited amount of memory, limited in general, and limiting the tape to only what the input occupies is what we're going to call a linear bounded automata. So no bound on the size of the input, but we're not allowed to use more memory than the input takes. So we're going to change and add a left end marker, think of it kind of like a bookend, and a right end marker, like a bookend to the end of the tape. And we cannot access anything outside of those bounds. We cannot rewrite or interact with the end markers. We can't go left from the left end marker, right from the right end marker, or use them for anything other than to say, this is a dead end, you cannot go past here. Assume it's non-deterministic, that doesn't change the class of languages that it can accept. And of course, we can still have multiple tracks, but each track has to be bounded to the same size as the first track. We'll give you an example. A linear bounded automata accepting the language a to the n factorial. So some number of a's that represents some factorial. So how would we do this? We're restricting the input to the size of the number of a's that are on the tape. So you don't have more space than that. But what if we did have access to a second track? What would you keep track of on that second track as you're parsing through these a's to determine whether or not the number of a's was some factorial?
The current, in the recursive algorithm, the current number. That makes sense.
Mm-hmm. What do we know about every factorial? Is it divisible by 2? If it's larger than 2 factorial, is it divisible by 3?
Yeah.
If it's larger than 3 factorial, is it divisible by 4? If you divide out 2, 3, and 4, and the factorial is divisible by 5, is the remainder of what's left divisible by 5?
It has to be.
Yes.
Yeah.
So what the second tape is going to count is the current divisor. Starts out at 2, then is 3, then 4, then 5. And we're going to go back and forth within that little window. Whenever we reset to the left, we're going to delete the current, we're going to keep the current character. And every time we move right, we're going to delete that character. As such, does that make sense? Let's give you an example of that because it's a little fun to visualize.
Yes, I think it would help.
Like,
Like, I think you can process this, but
So,
whiteboard.
a small factorial. 2 times 3 is 6 times 4. I don't want to draw 24. We'll go with 6. So we have A, and our second track is going to start out with 2 A's on it, representing 2. So we start on the left, and whenever we come back to the left, we're going to keep a character, which we already did. So we're going to move, we act like we just did that. So we're going to start here. And since we move right, we're going to delete that character. We see that this moves off and is the blank. So we reset, keep the next character, move right, that deletes that character. And we continue this process until we fall off. We see the right bookend here. So that deletes every other character. Then we reset this tape, add an A to this tape. And now we're going to, whenever we see an A, we're going to go over until we see the next A. So we start keeping this A, and we move right till we see the next one. Since we're moving right here, we delete that one. Since we move right here, we delete that one. we fall off the end, see the right bookend, so we're gonna reset here. And since we found the right bookend, as we go back over, we can check for how many A's are left. If it's fewer here than there were here, we're done. And if there's a single A left here, then it was a factorial. Because when we divide out something like 3 factorial, if we divide that by 2 and then divide that by 3, we should end up with 1 if it's a factorial and only a factorial. Otherwise, we get some partial answer here where this process doesn't complete. So if this 2-tape Turing machine ends with a marker here, and a single A on this tape, then it was a factorial. What factorial it was is the number of A's on the second tape.
How does the Turing machine know how many steps it should take on the first tape?
You just go until you see the next A. So you'd replace this A with some marker representing deleted. So not blank. It even could be blank in this particular case because you go until you see the bookends, not blank. So just something that represents was deleted. Doesn't really matter what it was, just add it to the tape alphabet. So that's an example of a language class that is in the linear bounded automata because we don't need more space than just the input on any particular tape. So for any particular sub-process. Think of this like how much space do you need in a particular method? If you were restricted to 5 statements in a particular method, you would be limited in the scope of what a particular method could do. And then you just wouldn't allow the methods to chain. Like at the end of one method, call the next one, pass in the result. And if you couldn't pass in the result, there was no communication between those methods. Then the length of the associated method, the complexity of that could only be up to and including 5 statements. Kind of a similar idea. Yeah, so in general, divide the number of A's on the tape by every possible next number. At the end of the process, there's a single A left on the tape, we accept. If at the end of one of those processes, we can't do the next process or the next process fails before getting to the end, where at the second tape, we didn't reach the end, the last A there, then we would reject. Second tape keeps track of the current divisor, and we kind of drew it out. We don't necessarily need to write the whole thing. The question I have for you, though, in general, is linear bounded automata more or less or equally powerful compared to not Turing machines, but NPDAs?
I'm inclined to say more, just because we don't have a limit of like where we can access memory.
Yeah. Is there anything interesting about the infinite memory of the stack? Yeah. That's the only interesting wrench that I think this throws in, yeah.
Well, like, just talking about like, what was the question? Powerful?
Yeah, can it recognize every language that an NPDA could recognize? In which case it would be equally powerful. Can it recognize all of those languages and then some additional languages? Could it not recognize languages that are context-free? In which case it might be less powerful or differently powerful if there could be a context-free language that it couldn't recognize and another language that isn't context-free that it could recognize. A tough question. Yeah.
I think it's yes, because you can like, it can be more powerful because you can display strings like A to the N, B to the N, C to the N by having 2 different types of storage that you can effectively use, like in the case previously.
Nice. Yeah.
And then basically now you have 2 stacks, so you can now check both of those. So you can do anything that you can do in a normal NPDA and also do more.
Yeah, that actually is right. And the reason it is right is that the stacks that we used for an NPDA only recognize the characters that were in the input. If we had an A to the N, B to the N, the most characters that could be on the stack was the length of the string. The bound on the size of that stack was the length of the string. So even though we had an infinite amount of storage on that stack, it was never more than what we actually used in that stack was never more than the length of the string. So because of that, we could simulate that within a linear bounded automata. How about unbounded Turing machines? More powerful, less powerful? Obviously, the answer is not going to be more powerful. We placed a restriction on it. The question is, does that restriction matter? So really, there are two. Are they equally powerful or less powerful? So the only two reasonable answers. But which one of those do you feel like is a more intuitive answer?
Intuitively, I would say less powerful because you have less memory, or because you can have less memory.
Yeah. Maybe classes of problems or types of problems that you don't think that this could solve.
Well, it kind of seems like, it's like non-deterministic, seems like the unbounded are kind of. I feel like it would just be the same, because if like a non-deterministic, but non-determined an NFA essentially do the same thing, DFA, the same language. And that kind of like relationship between these bounds in memory exists. There might be that same kind of relationship with this.
Yeah, that's a very intelligent way of thinking about it. The answer is less. The proof is kind of gross. But the way that I like to think of it is there are certainly classes of languages that require more memory than, it's not something that happens in a stack form, but a more complicated data structure, like a particular string going through a hashing function that is more complicated than that string's representation. That would take more memory to hash than the string did to represent. Or even, is this hashable with this function? So those kinds of questions. But yeah, the actual proof is in the book, but linear bounded automata is a subclass of unbounded Turing machines. But it's an interesting subclass, and we'll actually come back to it a little bit later with regards to what we can do with it. So keep that in the back pocket for the moment. Now that we've talked about some different language classes, we actually saw a slide from the slide deck a couple of weeks ago when somebody asked about how do we visualize how these different language classes relate to each other. That is the last couple of slides in this slide deck, so we'll get back to that. But now we've reached that point in the class where we've seen so many different language classes that it would be useful to actually think about how are these language classes related to each other. So classes on languages that a Turing machine can operate on, removing restrictions, all restrictions to grammars. We're going to start looking at even more complex language classes than just the base, what can a Turing machine accept and reject? So we talked about the countable and uncountable sets with the regards of something like countable. There's kind of an algorithm for that, for at least enumerating and continuing to do something useful. But let's talk about the two new language classes that are kind of outside the scope of what a Turing machine can halt and both accept and reject on. So do we agree that if I ask a Turing machine to do something like, I had a Turing machine for adding two unary numbers, something that we've done before, regardless of what I put on the tape, that program is going to complete. If we ask it to recognize the language A to the N, B to the N, and you give it a string, it will either say, yes, that string is in A to the N, B to the N, or no, that string is not in A to the N, B to the N. We're going to address the language classes where that's not necessarily true. There's some restriction on the Turing machine. So a language is recursively enumerable if a Turing machine can accept it, but we say nothing about what happens if we don't accept. So something like, we were able to write a procedure where if the string is in the language, we can answer yes in a finite amount of time. However, if the string is not in the language, there is no guarantee about whether the Turing machine will ever halt or not. It may just spin forever, trying to determine whether it is in the language. The answer is it's not, but there's no distinction between a string that is in the language, but takes 1,000,000 years to prove that it is, and a string that's not in the language, and after 1,000,000 years, it's still going to spin forever. After 1,000,000 years have elapsed, do we know which of those threads we're in? No. There's no way to determine an answer to that question. So we can allow Turing machines to go into an infinite loop and never halt. For a recursively enumerable language, every string in the language, Turing machine will accept it in some finite number of transitions, but we don't put a bound on that limit of that finite number of transitions. It could be millions, it could be quadrillions, it could be decillions. It could be such a high number that even with modern computers, it will not answer yes until the end of the earth as we know it. Strings not in the language, the Turing machine may reject it, or it may enter some kind of infinite loop. Not an infinite loop that we design necessarily, but an infinite loop that we need for it to be able to do something on every string. That's just part of the design of the Turing machine, is that that is a necessary component of recognizing this language. In order to be able to accept everything, we have to construct an infinite loop for some of those rejections. So that's the concept of recursively enumerable. Attach yourself to that word enumerable, because that means if the answer is yes, we can enumerate the yeses. And we'll talk about exactly how to do that. With recursive languages, then we can accept and reject in a finite number of steps. So this is the programs that we write that don't go into an infinite loop. So this means that there exists what we call a membership algorithm that's able to answer yes or no to the membership question that says, what are all of the strings that are in this language? And that process is capable of accepting and rejecting every possible string that is given to it. If it's recursively enumerable, we don't have a membership algorithm, because when we feed it a string that's not in the language, we have no way of that process terminating necessarily. So we will know yes or no any string constructed of characters in the input alphabet in a finite amount of time. There's, again, no guarantee on the length of that finite amount of time. It could be an arduous amount of time from our perspective, but what are we compared to big logical overlords? Questions I might have for you. First of all, any questions on the definitions of recursively enumerable or recursive? Does that make intuitive sense to people? Maybe some thumbs. So how do you feel about those definitions or those concepts? Yeah.
But it is like a squared rectangle, where it's like a recursive language might also be a regular.
Yes, yeah, recursive contains everything that we've talked about so far. Recursively enumerable now has something like, we can answer yes as to whether a particular number is rational, because we can eventually get there. But if I give you a real number, how would you ever show that it's not rational? You can continue to enumerate the rational numbers in the way that was shown, and that would, if it is a rational number, then it would spit it out. But if it's not rational, that process would never terminate. So we would have no way of showing that this number is real but not rational, because the process for rationality never terminates. But if it is rational, then we'll get there eventually. Does that make more sense? Does that help things make sense?
I was gonna ask a similar question, but your example of the proving that something isn't rational kind of answer.
Yeah. And I think that idea helps a lot. If we have a process that can answer yes, but can't answer no, we just don't know if we haven't gotten there yet. And especially with a procedure as arduous as that, kind of diagonal table for coming up with rational numbers, you can imagine, I just give you a really large rational number, really high numerator, really high denominator, like hundreds of millions of digits. How long would it take to iterate that diagonal table to come up with that very large but rational number? If we terminated this process after a minute and said, well, we haven't gotten an answer yet, so it's not rational, there is an existing rational number for which that conclusion would be wrong. If I let that process run for 1,000,000 years, there would still be a rational number for which the conclusion would be wrong. So you don't have an algorithm for it because we can't answer no.
That mean that if it is enumerable, there's always another way to find out how long it's gonna take, how many operations it would take.
Yes, if you have an idea of the structure, it's just that sometimes we don't have an idea of the structure, like for instance, the twin primes conjecture. We don't know the structure of the twin primes, so we can't come up with a function that allows us to say, given a particular number that I'm curious about, what is the next set of twin primes?
There's no pattern.
Right, not that we're aware of, not that we've found. Some way of calculating what is the next digit of pi without the associated context of every other prior digit. There's no pattern to it. So we can't have a function that generates it. We can with pi, because it's just successive division. But for something like the twin primes, there's no where is the next one going to be. We just keep looking and we keep finding them. So are recursively enumerable languages recursive? No. Why? For questions that we can answer yes to, but not no, and we answer yes and no to them. That's a fun way of rephrasing that question. It becomes a little bit more apparent when phrased that way. Are recursive languages recursively enumerable? This answer is yes. They're a strict subset. So for all languages we can answer both yes and no to in a finite amount of time, we could answer yes and just, if we would answer no, go into an infinite loop. And you would be able to simulate a recursively enumerable language with a recursive language. All right, I think we'll stop here for the day and we'll come back with more of how to enumerate these kinds of languages. I've actually kind of spoiled that already, but we'll go over it again, talking about it in terms of the actual language and Turing machine pair, rather than just the way that we've talked about it. And hopefully I will start to engage you more on this concept. It is very theoretical, but it's very fun to think about, I find, because there are real world consequences to all of these ideas. So I will see you on Monday for that. We're reviewing tomorrow, exam on Friday. So please come prepared with questions. I don't have any material prepared for tomorrow with regards to problems. So either bring your own problem you want me to solve, or tell me you want me to generate a problem, and I can come up with something. But other than that, you come with the content. I have office hours starting now.